Cauchy's integral formula. So in the Cauchy's integral formula, we are given three things. Okay, we are given an analytic function f of z, which is analytic in a simply connected domain D. Okay, and z naught is a complex number which belongs to the set D, or it is any point in D. Okay, and then what we do is we consider any simple closed path in D, and we make sure that it encloses z naught. Okay, very much like the question that we have discussed just now. All right. Now, the conclusion of the Cauchy's integral formula is this. If we have the integrand whose numerator is the analytic function f of z and whose denominator is z minus z naught. Okay, now see, now by making sure that f of z is analytic in a simply connected domain D, we are ensuring that this doesn't have the factor z minus z naught in it. Okay, fine. So if this is the integrand f of z upon z minus z naught, and if we have a curve C, a closed curve C, then the line integral of f of z upon z minus z naught with respect to z along curve C is actually equal to 2 pi I times f of z naught. Okay, see, now students often find the Cauchy's integral formula and the Cauchy's integral theorem to be confusing. Okay, this is because of the same notation that we use. Okay, even in the Cauchy's integral theorem we are using f of z, however there the whole integrand is f of z. Okay, so this is the situation for Cauchy's integral formula, and if we start talking about Cauchy's integral theorem, then here the integral itself is f of z. Okay, that is the main difference. Secondly, the right hand side. Okay, in the Cauchy's integral theorem the right hand side is always 0, and in the Cauchy's integral formula the right hand side is 2 pi I times the value of the function f, or the numerator of the integrand at the point z naught. Okay, now we are going to prove the Cauchy's integral formula using the theorem, Cauchy's integral theorem, as well as the ML inequality. Okay, all right, again we will take the help of path deformation. Okay, so suppose the given path is C, we will deform it. Okay, we will deform it into a circular path C prime such that the circular path C prime is centered at z naught. Okay, the point in the domain D. Okay, and let us construct an arbitrary circle as C prime and let its radius be rho. Okay, now because we have proved this already, after deformation we can still say that the integral's value will be same no matter whether we integrate it with respect to or along C or along C prime. Yes. Okay, now the next step is crucial. In this step what we are going to do is we are going to add and subtract f of z naught from the numerator of the integrand. If we do that, then we will get something like the following. Okay, we are going to split it so that in the first integrand we will get f of z naught in the numerator. Using the linearity property we can write the second integrand as f of z minus f of z naught upon z minus z naught. Okay, now because we have already proved this result, that 2 pi I into f of z naught, that is the integral that we obtained in our previous question, right? This one. If n takes the value -1, the value of the integral is 2 pi I. We can use this result and get the value of the first integral as 2 pi I times f of z naught, because f of z naught is a constant as far as z is concerned or f is concerned. Okay, so it is 2 pi I times f of z naught. Refer question 2. Alright, now the job is to evaluate this integrand. Alright, okay, now to evaluate this integrand or this integral, we will take the help of ML inequality. Okay, now by ML inequality we have the following: the absolute value of this integral I prime will be less than or equal to m upon rho into 2 pi rho. Well, 2 pi rho is the circumference now, or L. Okay, and how did I get rho in the denominator? We know that mod of z minus z naught is rho. Yes. Okay, and as far as the numerator is concerned, we will take m as the maximum of mod of f of z minus f of z naught on the circle C prime. Okay, now this actually allows us to cancel rho and gives the relation absolute value of the integral I prime, the second integral there, has to be less than or equal to 2 pi. Okay, now we know that 2 pi cannot be 0. However, because the function f of z is continuous, we have already assumed that it is analytic, so it has to be continuous. Now due to continuity, if you start reducing the radius of the circle, eventually the absolute value or the maximum absolute value of the difference f of z minus f of z naught, this will start approaching 0, and therefore the second integral will also approach 0. And if the second integral approaches 0, the blue integral, then the original integral approaches 2 pi I into f of z naught, and that is the Cauchy's integral formula. Okay, or the conclusion of the Cauchy's integral formula. Again, let me remind you that only the numerator here is analytic. Okay, and by considering z minus z naught in the denominator, we are deliberately introducing a pole in the integrand. Pole means a point where the function is not defined. Okay, now in this case the integrand is f of z upon z minus z naught, and the location of z naught is such that it is enclosed by the curve C. Okay, fine. So let us now solve problems based on the Cauchy's integral formula. Okay, all right, I think I have 2 questions. Okay, fine. Question 1 on Cauchy's integral formula. Here our job is to integrate 4z squared plus z upon z squared minus 1 with respect to z along closed curve C. Okay, and this closed curve is a circle centered at the point 1 plus 0 I, and the radius of the circle is 1 upon 2. Okay, now let us try to find out the location or the points where the function is not defined. Okay, the function means the integrand. Okay, now these singularities will be there when the denominator is 0. Yes, so equate z squared minus 1 to 0, which will give you two numbers or two roots, 1 and minus 1. Okay, now observe the following. If you substitute z equal to 1 in the equation of the curve, or left hand side of the equation of the curve, what will you get? You will get mod of 1 minus 1, which is 0. In fact, this is the center of the circle. Is it less than 1 by 2? So this point z equal to 1 lies inside. Okay, as you can see here, this blue dot. And for the second point, minus 1, if you substitute it in the left hand side of the equation, you will get it as 2, the absolute value, which is greater than 1 by 2, the radius of the circle C, and therefore this point lies outside the curve C. Which means we have to now split the denominator into partial fractions. Okay, because we are only interested in the point 1 comma 0 or 1 plus 0i, and not in the other point minus 1. Okay, so this is how we proceed. We can solve the problem by two methods. Method 2 is a better one, but let us first solve it by the method of partial fractions. Okay, so to do this, we consider the function 1 upon z squared minus 1, and we split it into partial fractions whose denominators are z plus 1 and z minus 1 respectively. Okay, now I'll not explain how to obtain the coefficients here. For 1 upon z plus 1, the coefficient is minus 1 upon 2, and for the second one, the coefficient is going to be positive 1 upon 2. Okay, all right. So let's not forget also that we have a function in the numerator as well, 4z squared plus z. Okay, so now what I'll do is I'll use the linearity property, and I will split the integrand with different denominators. Okay, so first integrand will be 4z squared plus z upon z plus 1 into minus 1 upon 2. Now as far as this integrand is concerned, the value of the integral is equal to 0 because of the Cauchy's integral theorem. Why? Because this function possesses only one pole or one point where the function is not defined, and that point is minus 1. Okay, but this point is something which lies outside the circular region or the curve of integration C. Yes, so we can happily apply the Cauchy's integral theorem because our integrand is analytic on the curve as well as inside the curve. Okay, so that integrand straight away is 0, or the integral. Now for the second one, let's try to make use of the Cauchy's integral formula. Okay, first you can take this 1 upon 2 outside. Okay, and now observe that in the notations of Cauchy's integral formula, z0 is 1 and f of z is 4z squared plus z. Okay, so it is 2 pi I times f of z0 by the Cauchy's integral formula. Yes, so substitute z equal to 1 or z0 equal to z0, which is 1, in the function, which will then give you the integral's value as 5 times pi times I. Okay, this 2 and this 2 will get cancelled. Cauchy's integral formula. Okay, so cancellation of 2 will give you 5 times pi times I. So that is the final answer. Okay, see now the significance of these formulas as far as problem solving is concerned is that we are not really integrating. Okay, in the sense that we are not finding the antiderivatives of these functions. Okay, all right, let us solve this problem now by the second method, which is much better. Okay, so this time what we do is we, after identifying the point at which the function is not defined and that point lies inside the and the point lying inside the curve C, we only keep that particular term in the original denominator in the new integrand's denominator, okay, or z minus 1, okay, and all other factors of the function, if there are any, which correspond to locations outside C, we include them in the numerator. Okay, so this time z0 still remains 1, but f of z changes, okay, from 4z squared plus z to 4z squared plus z upon z plus 1. Okay, so now our job is to substitute z equal to z0, which is 1, in the function f of z and apply the Cauchy's integral formula. Okay, so you'll say by the Cauchy's integral formula, required integral will be equal to 2 pi I times the value of the function, or the numerator in this case, at 1. Okay, so 4 into 1 squared plus 1 upon 1 plus 1, 4 plus 1 5, 1 plus 1 2, again 2 will get cancelled and you will get 5 pi I. Okay, fine. Let's go to question 2. In this question, we are defining f of z0 by the line integral of 3z cubed plus 5z plus 2 upon z minus z0. Okay, and C is our contour of integration or curve, which is the ellipse in the z plane. X squared upon 4 plus y squared upon 9 equal to 1. Okay, and our job is to now find f of 1 and f of 4i. Okay, now it's not very difficult to find out that if we let z to be 1, okay, then this point 1 comma 0 is lying or it will lie inside the ellipse. Yes, so if it lies inside the ellipse, we can not apply the Cauchy's integral theorem, but we have to apply the Cauchy's integral formula. Therefore, by application of the Cauchy's integral formula, we have to take z0 as 1 and f of z as 3z cubed plus 5z plus 2. Okay, and we have to substitute z equal to 1 in the definition of the function. Okay, so after substituting, we will get f of 1 as 2 pi I times f of z0, 3 into 1 plus 5 into 1 plus 2, 7 plus 3 10, 10 into 2 20. So the value of the function at 1 is 20 pi I. Okay, now let us try to do the same thing for 4i. Now 4i is a point which lies on the positive side of the imaginary axis or y-axis. Yes, and it corresponds to the point 0 comma 4 in the z plane. Now this point lies outside the ellipse or C. So we can now apply the Cauchy's integral theorem and say that the value of the function at this particular point is going to be 0. By Cauchy's integral theorem, and for this we may say by Cauchy's integral formula. Okay, now quite often it so happens that our integrand consists of multiple factors of z minus z. Okay, so we will now try to find out whether there exists a way to find such integrals. Okay, notice that the only difference between the pole of this function and the pole of this function is the order. Okay, the location of both the poles or location of the pole of both the functions is same. The only difference is here we say that the pole is of order 1 because the power of z minus z naught is 1, and here we say that the pole is of order n because the power of z minus z naught is n. Okay, and we also assume that f of z doesn't have any factor of z minus z naught. Okay, so we will now modify our Cauchy's integral formula and obtain a more general result. And you can actually prove this by Leibniz formula. Okay, or Leibniz rule, which is also known as DUIS, or differentiation under the integral sign, where the ordinary derivative becomes partial derivative. So let us accept this formula without proof. Okay, so this is what the formula has to say, and this is one of the ways to find the derivatives of analytic functions. Okay, so everything here is same, meaning all the things that are given to us are the same, but there is only one change. Okay, and that change is in the power of z minus z naught. In the Cauchy's integral formula, the power of z minus z naught was 1, and here we have powers starting from 2. Okay, note that it is n plus 1. So according to this formula, what we have is, if the integrand is in the form f of z divided by z minus z naught to the power n plus 1, okay, then this is equal to 2 pi I times the nth derivative of the function f with respect to z evaluated at z naught into 1 over n factorial. So we have to be sure that we are finding the nth derivative and dividing it by n factorial. That's the reason we write it as n plus 1 and not n. Okay, so if you write this as n, then this will become n minus 1th derivative of f, and this will then become n minus 1 factorial. Okay, so you can keep any of these two versions of the same formula in mind, and if you substitute n equal to 0, you will get back the original formula. Okay, 2 pi I times f of z naught, because 0 factorial is 1 and the 0th derivative is the function itself. Okay, so now let us solve some problems based on this formula, and you can see that this formula is much better than this, because this allows us to solve problems which cannot be solved by the Cauchy's integral formula. For example, if you have let us say if you have z plus 1 raised to 2 or z minus 1 raised to 2, for instance. Okay, here we only had z minus 1, so what if we have z minus 1 raised to 2? Okay, and for that, not the formula but its generalization comes to our rescue. Okay, so you can have any index here now, any positive integral index. Okay, so let us solve problems based on the modified formula or the general formula. Question 1. In this question, the denominator is z minus pi by 4 to the power 3, and the numerator is z squared plus cos squared z, and the curve C is the unit circle yet again. Okay, now we have to first find the relative location of the point pi by 4 where the function is not defined or the integrand is not defined relative to unit circle. Okay, now of course pi by 4 is a number which is less than 1 because pi is less than 4. Okay, so clearly mod of pi by 4 will be less than 1, so the point z equal to pi by 4 lies inside C. So we cannot really apply the Cauchy's integral theorem, but we can still apply the modified version of the Cauchy's integral formula. Okay, and to do this we will write down everything in our usual notation. Okay, Now z0 is pi by 4, very easy to identify. F of z, z squared plus cos squared z. Yes, okay. And now is the time to make the appropriate choice for n. Okay, remember in our formula we have written the power of the denominator as n plus 1. So if you now take n plus 1 as 3 here, it will give you n as 2, which means we will be required to find the second derivative of the function f of z and put z as pi by 4. Okay, so let us do that. What will the integral be? The integral's value will be 2 pi I times n factorial multiplied by nth derivative of the function f at z0. Okay, so it is 2 pi I upon 2 factorial into second derivative of the function at z0, which is pi by 4. Okay, so this is going to be pi I times second derivative of the function at pi by 4. F of z is z squared plus cos squared z. First derivative of z squared is 2z, second derivative 2. First derivative of cos squared z is 2 cos z into minus sin z, which is minus sin 2z, double angle formula, and again differentiate this, you will get minus 2 cos 2z. Okay, substitute z as pi by 4, and because cos pi by 2 is 0, the integral's value is going to be 2 pi I. Okay, because the first term is 2 and the second term is 0. Alright, so this is how you apply the general version of this formula. Let us now solve one more problem. Using the Cauchy integral formula, find the value of the integral of z plus 3i upon z squared minus iz plus 2 to the power 3 with respect to z, where C is the circle, mod of z minus 1 minus 2i equal to 2, which is oriented in the anticlockwise direction. Okay, first let us try to find out those points where the denominator of our integrand is 0, or at those points where the function is not defined. Okay, the poles or singularities. For this, go to the denominator and equate it to 0, because this is now a rational function. Okay, now this equation when solved produces the roots as 2i and minus I, minus b, so plus I, plus or minus root of b squared minus 1 minus 4ac, so minus 8. So effectively you are getting I times plus or minus I plus or minus root of minus 9 or 3i. Okay, so the first root is going to be 2i considering positive sign, second root will be minus I considering the negative sign. Okay, now we have to determine the relative positions of these points, these 2 points, with respect to or relative to the curve C. Okay, fine. Now we can easily do that by substituting z as z1 and z2 in the equation of the or the left hand side of the equation of the curve C. Okay, if we get a number which is less than this number, it means that the point lies inside C. Okay, so let us now do it for 2i. 2i minus 2i will get you 0, and mod of minus 1 is 1, which is less than 2, so z1 lies inside C. So we can definitely not apply the Cauchy's integral theorem. Okay, now what if we substitute z2 there, okay, or minus I? So then we will get the complex number minus 1 minus 3i, yes, whose absolute value is or modulus root of 1 plus 9, which is root 10, which is definitely greater than 2, so z2 lies outside. Okay, so as far as the application of Cauchy's integral formula is concerned, it is required to consider only the root z1 or 2i, okay, which lies inside the contour C. Okay, so this time instead of splitting this into partial fractions, this is what we can do. Okay, we can readjust the terms in the integrand so that only that factor remains in the denominator which is associated with the pole that lies inside the contour C. Okay, what was the root? The associated root is 2i, So only keep z minus 2i in the denominator, and the other factor of the quadratic expression, which is z minus minus i or z plus I, put it in the numerator. So this is now going to be our f of z. Okay, all right, and now we can apply the formula right away. Z naught is 2i. Yes, f of z is the remaining part of the integrand, excluding the factor z minus 2i to the power 3, z plus 3i upon z plus I raised to 3. Yes, and n plus 1 is 3, so n must be 2. Okay, now the integral, or the value of the integral, should therefore be 2 pi I times n factorial into nth derivative of the function at z naught. Okay, so again 2 factorial and 2 will go, so it will be pi I times the second derivative of the function at 2i. Okay, what is the function? The function is z plus 3i upon z plus I raised to 3, and to find the second derivative, what I have done is I have split it into two rational functions. Observe that 3i can be split into I and 2i. So do that, and this is what you will get. First you write z plus I, and second you write plus 2i. Okay, so this allows us to get the two rational functions, first as 1 upon z plus I raised to 2, and the second as 1 upon z plus I to the power 3 into 2i. Much easier to differentiate now. Alright, first derivative. Derivative of 1 upon z plus I to the power 2 will be minus 2 times 1 upon z plus I raised to 3. Yes. 2i constant, let it be there as it is. Derivative of 1 upon z plus I to the power 3 is minus 3 into 1 upon z plus I to the power 4. Yes, okay. Differentiate it one more time to get the second derivative, because n is 2. Okay. Minus 2 into minus 3, 6. Denominator z plus I to the power 4. Minus 3 into minus 4 is 12. Denominator will be z plus I to the power 5. Don't forget 2i. Okay. Now is the time to substitute z as 2i. Okay. Put it here. You will get 3i to the power 4. I to the power 4 is 1. 3 to the power 4 is 81. Okay. Then substitute 2i here. Okay, so we have got 3i to the power 5. I to the power 5 is I, and 3 to the power 5 is, I guess, 243. Okay, yes. And then you can cancel I and get the value of the integral as 6 upon 81 plus 24 upon 3 to the power 5, which turns out to be 14 upon 81. Okay, so surprisingly the second derivative's value turns out to be 14 by 81. So the integral's value is, well, sorry, sometimes what happens is in the excitement of calculating the second derivative value, we just write this itself to be the value of the integral. Okay, but don't do that, please don't do that. Okay, this is the second derivative's value, and in the formula it is the first term here, and we have to multiply it by pi I. Okay, yes, so the integral's value is 14 upon 81 into pi I.